Okay, welcome everybody. Thank you for joining us today for our webinar with the topic of multiphysics motor design and optimization. So just a quick presentation, introduction of the presenters so you know who you'll be hearing from today. I'm your host, Anthony Larella. I'll be introducing kind of the presenters and Maya in general, and then I'll pass it over to my colleagues, Anthony Lowther and David Stevens, to take us through more of the technical content of today's webinar. All of us are pre-sales specialists at Maya with varying disciplines as far as what we cover, from EMAG to CFD to system simulation. As far as Maya in general, just in terms of a general introduction, at Maya HDT, we help organizations with their digital transformation journey. So Siemens has actually recognized us as a top global partner in 2022. And beyond that, we're not just experts in consulting and systems integration. We're also software developers with over 30 modules authored for Siemens and used by millions worldwide. In terms of the team at Maya, 75% of us are scientists and engineers with actual hands-on experience across nearly every industry. So whether an organization is looking to better design, simulate, manufacture, or optimize operations, we, being Maya HDT's combined engineering, software development, and AI expertise, are uniquely positioned to help you move from concept to completion and beyond. So after having said that, I'll pass things over to Anthony Lowther, who will take us through the first part of the presentation here.
Okay, so hopefully you all know what you're here for, but this is a slightly more detailed breakdown of how the presentation is going to go today. So first, we'll just sort of do a quick overview of what physics domains are applicable to electric motor simulation, and we'll talk about which ones we'll be looking at today. Have a brief overview of the electric motor development process. Many of you are familiar with this, will have seen this before, but we'll just make sure that everyone's sort of on the same page. We'll also mention what tools we're using and how we're going to be using them for today's presentation. We'll then go over the optimization of the electric motor model and how we went about that. Look at the thermal design and the optimization for the thermal capabilities, and just a quick overview of how we can expand this beyond today. We're just looking at electromagnetics and thermal, but how we expand into further domains using the Siemens tools and Maya's expertise in them. So to introduce the platform of tools that we're using today, we're primarily going to be using the Siemens Simcenter simulation platform. This is a collection of tools, the center piece of which is called Simcenter 3D, but it also includes a number of other simulation tools. And this just allows us, as a family of tools that work together, to easily integrate our designs, moving from one phase to another, from one physics domain to another. This covers everything from electromagnetics and thermals that we'll talk about today, acoustics and structures, dynamics, etc. You can see all of that on this slide. It also covers things like automation, 1D and system simulation, and other such areas. So when we're looking at motor design, there's four primary physics domains that we really tend to care about. First is the electromagnetics, which really are just the underlying physics driving motor performance, driving the results of every other physics domain. From the results in the electromagnetic space, we can look at losses, which push into thermals. We can look at forces, which might have effects in the mechanical and acoustic domains, which are the other areas that we could be interested in. So from a thermal perspective, obviously we care about how hot things get for a number of reasons. Thermals can affect the performance of a machine, but they can also put the materials in the machine itself at risk. So oftentimes, especially these days with higher energy density machines, smaller machines, having to be in places that are possibly not ideal, we do have to care about cooling quite a lot. Mechanically, a motor is great, but if it tears itself to shreds when it tries to spin, that's not so hot. So we're going to, or it won't be getting very hot because it'll be in pieces. We can look at the mechanical stresses in a machine. We can look at the forces coming out of electromagnetics and see how that affects the mechanical structures, whether that's the stator and rotor structures that we look at in electromagnetics, but also things like the housing of a machine and what it's connected to. Going on from mechanical, we can also expand that and start looking at things like acoustic performance and vibration analysis. This is important, especially in workspaces where there might be noise limitations, or in things like electric vehicles, which are increasingly popular, increasingly important today, but we can't have them running around sounding like jet engines all the time. So we have a quick poll question for you guys. Obviously today we're talking a lot about electromagnetics and thermals, but I'm curious to hear from you what sort of domains you focus on. So we've got 3 options here for you guys to select from: the electromagnetics, the thermals, the mechanicals, the acoustics. Maybe you focus on something totally else that I haven't even touched, and you can put that in chat and let us know what else you look at.
Yeah, and just a quick note on that, we will have time to cover any kind of questions towards the end of today's session. But if, of course, there are any clarifications that are needed, please feel free to include those too.
Okay, so we've finished taking some polls, and actually, okay, so thermals and mechanical analysis seems fairly important. Obviously, electromagnetic, everyone tends to care about. Acoustics, I guess from anecdotally, I'm surprised that it's not higher up on the list, but that's good. Today we're talking about thermals a lot, so hopefully at least 77% of you will vaguely be interested. So when we're talking about thermals, why are thermals important? Most of you will know this, but as a motor runs, you generate losses, things heat up, and higher operating temperatures can have some pretty negative effects. The most immediate of which that we notice is often a degradation in performance. You can see just between operating at 60 degrees, which is warm, all the way up to 120 degrees. This example, axial flux machine that we had, lost 30% of its torque, which is pretty massive if you're driving a car around and you suddenly lose a third of your power. As temperatures get more and more extreme, we start risking other permanent damage. We're not just going to lose torque because things are hot, we're going to lose torque possibly because we cause demagnetization in our machine, or we might cause coils or insulation materials to start to degrade. This damage adds up over time, and over the lifetime of a machine, you can see serious degradation in performance. So often when we're talking about thermals, we're talking about maintaining performance in the short term, keeping things cool, but also in the long term to avoid problems with the materials when we move forward. So how do we simulate cooling? There's a couple different ways we sort of look at cooling. Obviously, this is all driven by losses in the electromagnetic simulation. This is where the vast majority of heat generation comes from in an electric machine. And there's 2 ways we can use those loss numbers to generate thermal values. We can do rapid analysis, and the 2 ways we often see this done is equivalent circuit analysis. So we'll have a thermal equivalent circuit or lump parameter network that we put in some loss numbers, run it, and see how it comes out. That tends to be very, very quick, but very, very rough in terms of accuracy. We can do a basic thermal analysis with thermal transfer coefficients. So this is a slightly more detailed design or slightly more detailed simulation where we're going to look at the losses, how things spread in the individual components. But we're not going to do a CFD, which can be fairly computationally expensive, fairly time expensive, and we'll just substitute in that with thermal transfer coefficient. So effectively, how easily the heat energy can transfer between components. The most detailed way, of course, is to run a CFD analysis. This gives us a lot of freedom to play with cooling solutions. It gives us a lot of accuracy, results that we can be very, very confident in. But these can be complex to set up. They can take time to run. And often we try and avoid doing too many CFD analyses if we're trying to get through a project fairly efficiently. So let's quickly look at the motor development process. Many of you will have seen a V diagram or a process diagram before, where we might start with something like operational requirements. This could come from a system simulation. It could come from customer or other demands. You might just have a spec sheet that says, hey, we want a motor that does this. You can then often move into initial motor design. This is typically done, could be done template based. It could be 2D electromagnetic analysis. And this is just to get a rough idea, hey, if we build a machine of this shape, roughly how's it going to perform? And that gets you pretty close. You can then proceed into detailed motor design. This might expand into a 3D electric model, more detailed analysis. Maybe we've got some funny things going on in the geometry that we're trying to look at, things like end windings that only really show up when you look at a 3D model. And of course, we can start looking at multi-physics designs where we're looking at losses, we're looking at vibrations and forces, etc. All of this, of course, has to tie in back to validation and verification. So whether that's on a test bench, whether that's in a prototype machine, all of this needs to tie back into reality. And oftentimes, all this information goes back and forth. It's not a linear process. Information from one stage, it might force redesigns at an earlier stage to revisit our choices. As we mentioned, Simcenter is a fairly large portfolio. And in this case, there's a handful of tools in the Simcenter portfolio that help at each stage of the design. AimSim helping at system level simulation. MotorSolve is a template-based electromagnetic machine design tool. Simcenter Magnet and Simcenter 3D are larger tools that allow 3D electromagnetic analysis, as well as further multi-physics analysis in Simcenter 3D. For today's presentation, we're going to focus mostly on using MotorSolve to do a template-based optimization of an electric machine. And then we're going to jump right over to detailed electromagnetic design and talk about the thermal CFD simulation of our design and how that's been implemented and how we see improvements based on our EMAG optimization. To drive the optimization that we're doing today, we're going to use another Siemens Simcenter tool called Simcenter HEADS. Now, HEADS is an automation tool. It doesn't do simulations in and of itself, but it allows us to connect to Simcenter tools, to third-party tools. Anything that can be scripted can be connected to it, and it has a number of predefined connections, especially to Siemens tools and a couple of others. Using this, we'll be able to take a template-based object or a parameterized object. So in the case of Simcenter MotorSolve, where everything is already templated, we can give a number of values. Here's what we want to change, here's what we want to explore, and HEADS can go off and automate those changes, automate the creation of a new design, simulation of the design, taking out the results, and then do optimization or exploration as we need on that process. HEADS can also connect multiple tools together. So we could connect our electromagnetic simulation to a CFD simulation, take those lost results out of the electromagnetic realm, put them into the thermal realm, and use the thermal results out of that to drive an optimization process. Today, we're going to be using this to look at taking a basic motor design that we already had. We're going to look to maximize the power and efficiency that we get out without changing the overall geometry. we've got minimum, we have to impose some constraints around minimum torque and initial temperatures. And we are mostly looking at modifying magnet geometry and the coil powering. So now about a quarter of the way through our time slot, we get into the fun of what we're going to be looking at, which is the optimization of the electric machine, how we've set it up, and how we're going to look at the thermal design. So overall, the workflow is fairly simple in this case. We're going to build an initial motor design in Simcenter MotorSolve. We're going to connect that into Simcenter HEEDS and let HEEDS do its thing. Once it's solved a number of potential variants on our base design, we can take a look at all the different designs and some correlations that HEEDS will have pulled out, how certain variables that we've adjusted might have impacted our performance. From there, we can take a model design, we can pass it off into thermal, in which case we're going to be using Simcenter 3D FLOEFD. At this point, my colleague David will take over and explain how the CFD process worked, how everything was set up. After thermal analysis, we can bring all that information about temperatures back into our EMAG tool, in this case Simcenter MotorSolve, where we'll do a final design validation, make sure that what we think should happen is happening. So when we're looking at motor design in the EMAG space, particularly a template-based system like MotorSolve, there's a few stages that we go through. Initially, we need to find a way of defining our targets, our intentions. So as we said earlier, this might come from system simulation or data sheets. There might be customer requests or demands put on a designer. From here, we can quickly define our machine. We might be looking at things like numbers of slots and poles. We know dimensions. We might have constraints on power limits or controls and thermals and materials that we have access to. Once we've defined the overall machine and get into a little bit more detail in the design, we're talking about details in the rotor and stator, the windings, the drive mechanisms, the wire sizing, all of these detailed designs to set up the specific machine that we're trying to simulate. Once we have a design, a lot of the time we're looking to get some useful information out, not just raw results. This is where a specific tool like Simcenter MotorSolve comes into its own, where it's got pre-canned experiments and pre-canned plots that are of use to a motor designer. Things like efficiency maps and torque speed curves, where you're not having to do post-processing yourself on electromagnetic results that are just tons and tons of data. It gives you a nice plot right at the start. MotorSolve also has a basic thermal analysis using heat transfer coefficients. As we mentioned earlier, this doesn't do CFD, but it does do a more detailed thermal analysis than just equivalent circuits. Often at this point, we loop back, we do some verification or optimization based on our final results to go redefine or redesign our machine. In this case, this is what's going to be driven by Simcenter HEEDS, this bottom loop of verification optimization. And with it being automated means that we don't have to be there babysitting each step of the way. So I guess an open question to everyone who's here is, how do you come across your initial designs? Do you tend to get requests from customers? Do you have existing design specs? Are you modifying an existing design? One of the options that we've put up on this poll is other. If you choose other, we'd really be curious to hear how you come across your initial specs. And you can put that into the chat box and yeah, just let us know how you come across it. Okay, looks like we're about halfway. Most people have voted at this point. We'll give you guys another sort of 15, 20 seconds to submit. We don't want to waste too much time just looking at a poll sheet. Excuse me. Okay. Right. Existing designs. Yeah, I mean, a lot of time people have designs that have existed for a long time and they need redesigning, reevaluating. I am curious for the 8% of you that voted for other. I'm really curious to hear where you come, where your initial design comes from. So if you want to throw that in the chat box, I'd be really curious. So for our initial design, we used the model that we already had here. This is loosely based on a small EV motor. So it's an 8-pole, 48-slot interior permanent magnet machine, looking to generate somewhere in the order of 30 kilowatts of power at about 5,000 RPM. That's what this initial design was spec'd out for. It just about met that spec. We're looking for about 95% efficiency at full load, or better, obviously, if we can. And based on the magnet materials that we had chosen, or had been chosen for this design, we need to keep the magnets under 393 degrees Kelvin. And this is just the point that was chosen by the designers as where we could see problems for demagnetization. That's just to protect the material itself. So we have a couple parameters that we can adjust. The magnet width and depth, so effectively rectangular magnets, their geometry, as well as the magnet cavity geometry. So we can change the orientation, the placement, the dimensions. We've also allowed the optimization tool to push up the current. The initial design was spec'd for a slightly lower current than the chosen power supply could supply if necessary. So we've allowed the design, should it have the headroom, to push up the rated current. Obviously, it's a little easier to get more power out of it, but you're also risking extra losses, extra heat, extra temperature. So, as we mentioned earlier, we're targeting a couple things. We're targeting increased power and torque coming out of the machine. We want to make sure the efficiency is as good as possible, which implies that we're minimizing the losses. And particularly, we want to minimize the magnet temperatures to protect those magnets from demagnetization. We've had to constrain our drive system to 380 amps. That's what our chosen electronics were capable of. And we've got some geometric constraints for the magnets, just in terms of what's available to us, or what would be available to a manufacturer from our particular supplier, and just in terms of practicality. So you can see briefly on the right-hand side, we'll see this animation again, a number of different designs that were considered by the optimization tool. So I guess the highlighting here is not quite ideal. We're going to move from the initial design and optimization. We've looked at putting our basic design for motor solve and how we're going to talk to heats. The next step is to review that optimization and the results that we got from our design. So to set up the optimization process, I guess just to go over it fairly quickly for you guys, since we've talked about the design variables that we're concerned with. HEEDS has a MotorSolve portal. That means that HEEDS knows how to read in MotorSolve save files. It knows how to modify them, how to read out results, and how to basically rerun analyses. So using the built-in portal, it's really easy. Once we've got a base design saved in a MotorSolve file, push it into HEEDS. HEEDS reads it in, goes, hey, we know what kind of machine this is. We know what these results mean. How do you want to set it up? And it quickly allows us to select inputs, so our variables that we want to change, allowable ranges. We can define targets based on outputs, constraints, either on inputs or outputs. And we can choose an exploration strategy. And HEEDS allows us to choose a number of different exploration strategies, including a patented Sherpa strategy. If you're curious about how HEEDS goes about this, there's way more information online, or drop us a question. We can talk a little bit more towards it as we get to the end of the presentation. In C, we had a whole bunch of input and output variables here called variables and responses that we allowed. So as we mentioned, the magnet geometry and the cavity geometry. We were interested in terms of outputs, the efficiency, the power out, losses, and temperatures in the magnets, with a couple of constraints, as we mentioned earlier. Overall, we kicked this off and let it run overnight. And in about 19 hours, there were 61 potential variants explored. A couple of them generated errors. That's typically just from invalid designs. Your magnet doesn't fit in its cavity, sort of thing. Again, HEEDS is an optimization tool. Without a little help, it doesn't necessarily know what's wrong, but when it tries to put the design into MotorSolve, it'll quickly throw an error, and HEEDS can go, okay, that's invalid, we'll just move on to the next. The yellow infeasible designs that we see listed here, those are ones that didn't meet one of our constraints. So the torque was too low, the temperature too high, that sort of thing. Overall, this took about 18, 19 minutes per design that we analyzed. And this included both electromagnetic analysis and the basic initial thermal analysis. We skipped the thermal, it would run a little quicker, but we wouldn't have those initial temperatures. And this was all run on a single core, on a single license, on actually my personal workstation, just running it overnight when I wasn't using the MotorSolve license. So here, as we watched the number of designs, you can see that HEEDS was playing a lot with different shapes, particularly in the magnets and the cavities, bending things. You can see across the top as the different winding phase resistances changed because geometry is changing around the end windings, and how the magnets started to change things. By and large, we left the winding layouts to be the same so that we had one-to-one comparisons back and forth. Once this optimization was done, we found there were a couple correlations. Of course, once you've designed 60-odd different designs, run simulations on them, you can start to look for trends and information that could inform further design decisions or further exploration decisions. So some of the interesting, well, some of them more obvious than others, outcomes that we got to see here. We have a huge correlation, this big blue bar in the middle of our screen. That's the correlation between efficiency and magnet width. So as the magnet width increased, the efficiency went up, and that was a fairly tight correlation between them. We also saw a fairly good correlation both between magnet width and magnet thickness, these pairs of bars here, with magnet temperature. So a larger magnet, while more costly and other implications, does help to keep the magnet temperature down. Something that we did notice that I guess was not totally expected by me was that the cavity geometry had a negligible effect on any of our interested results. So no matter how those magnets were oriented, size trumped everything. And as you can see, there's way more correlations, and there's a handful of different ways of visualizing these correlations inside HEEDS once you've run a study. And these can, of course, help inform your next stages of exploration or next stages of design. The outcome after 60 different designs that were trialed, we found the efficiency of our design went up 2%. The output power went up 44%. A lot of this is attributed just because we could put more current through. We were a little bit more efficient. We could push quite a bit more current, and suddenly we generate a lot more output power. That's great. Actually, at the same time, our total losses went down 12%. And as we said, a lot of the changes that we saw in here were mostly magnet geometry. So in this case, we were just trying to optimize our torque, our power output, our losses. But you could even do things like trying to optimize to maintain performance while minimizing the mass of, say, your magnets or your steel in the machine. The next step from here, of course, was to start looking at the thermals of the machine. So for this, I leaned on my colleague, David. David took my results, took my design, and went off to do a wonderful job on the CFD analysis. So I'll let him talk about that.
Yes, thank you, Anthony. So yeah, as Anthony said, he gave me his information from his optimized model, and we did a conjugate heat transfer analysis. And the first thing we'll look at is what that workflow looks like. So we have the motor solve solution, which then outputs a simple geometry profile. So it's a simple DXF file in a sketch that's then imported into Simcenter NX. He also gives me the loss data for all of the bulk components within the machine. So between those two, we go into Siemens NX. We do just a simple extruded model of the motor geometry. So just using that basic sketch profile, we do a simple extrude in order to create solid geometry with all of the components in separate bodies. And as I mentioned, this was done in Siemens NX. From there, I did create a basic cooling jacket design that you can see on the outside there that's a bit transparent, where you have flow coming in actually at the top of the machine or bottom of the machine, depending on how it's oriented. And that flow then flows circumferentially both sides of the motor down to the bottom where it exits. And that's a water cooling flow. So for this, the conjugate heat transfer analysis was performed in Simcenter FLOEFD, which is a designer definitely a designer-based and oriented CFD tool, as well as thermal tool. It also has some structural capabilities as well. This flavor was done in Siemens NX, but FLOEFD is also available in CAD tools such as Solid Edge, CATIA, Creo, as well as a standalone version. So we have two fluid domains for this model. We have the rotor stator gap, which is just an air gap in the machine between the rotor and the stator. And then we have the cooling flow, which is a water domain. And then we also have the solid domain for conduction. So in this model, we're just modeling fluid flow and conduction. We're not including any type of radiation effects or anything like that. We can go ahead and move forward. Model details, and this I did a simple quarter symmetry design. The cooling jacket allowed me to reduce the model to that because of the dual water flow inputs on either side of the motor, as well as the dual water exits. This is a fairly large model, especially for FLOEFD, so on the larger side. So we're looking at 19 million total cells, about half fluid and half solid. And really the majority of those cells, they're kind of bunched up together here. But if you look at the rotor stator gap, you have to have some quite small cells in there to get the heat transfer accurately modeled there. And one assumption that was made here was that there was no heat loss from the ends of the motor. All of the heat had to be transferred via convection from the rotor to the stator. This model used a K epsilon turbulence model with modified wall functions. So we're not fully resolving the viscous sublayer here. We're relying on wall functions, which is kind of a strength of FLOEFD when you're doing a design-based analysis, where this is essentially a first pass for this thermal analysis. We're not having to do some real small cells at the viscous sublayer. FLOEFD does have a second order spatial discretization, and the solution time for this for one run was about 11 hours on 22 cores. As I said, it's a fairly good sized model. One way we could have reduced this down and maybe done some more runs with this model, or maybe a submodel, would be using a sector and then applying just a simple heat transfer coefficient instead of including the water jacket. But in this case, we wanted to show how a water jacket could be incorporated. Go ahead to the next slide. Our boundary conditions. So we have our cooling flow shown where we have a quarter kilogram per second of water flow through the system, and with an inlet temperature of 273 K, which is about room temperature. For this first order analysis, that's sufficient. Maybe if we were to iterate a bit more, we might want to increase that a bit more to include some whatever you're going to be cooling that with, to whatever that minimum temperature would be. We have a simple outlet pressure of atmospheric for the water. just to be able to see our pressure drop. The main thing we have here is for the rotor and stator is we have a rotating wall at 5,000 RPM, so it's considered a stationary model in the solid domains, but we still have the convective cooling effect of the rotation. As I mentioned previously, that the ends of the motor are adiabatic, and that's a more conservative approach to assume, okay, we're not losing any heat from the ends of the motor, and all of it has to be transferred through the rotor stator gap. And as I mentioned previously, we also have a symmetry on the YZ plane and the motor longitudinal plane to reduce the model size. You can go ahead to the next slide. So the applied heat losses that I've received from Anthony from MotorSolve are shown here in this table, and you can see how they were applied at the stator back iron, the windings, the stator teeth, the rotor back iron, and the magnets. And you can see the pre and post optimization values for that. And these were just volumetrically applied heat loads, and they were divided between the solid bodies on a volumetric average or weighted base. Go to the next one. So our results for our solid temperatures, we saw a fairly modest reduction in these values. And however, at first, I'm not a electromagnetics guy, and one of my first questions for Anthony was, okay, we see a modest decrease in temperatures here. What are the effects? But we do see some pretty large gains, in temperature decrease, and especially in the magnets and in the rotor back iron. Go ahead. Next one.
Really useful. Much better explanation of the CFD and thermal analysis than I could have given. I'm fairly hand wavy at this stuff. As David mentioned, sort of one of the big things we were looking at, and it was mentioned earlier, is that we wanted to keep those magnets nice and cool. And to see a nearly 3-degree drop in the magnets isn't huge, but it is substantial enough to warrant consideration. And so what we did was to know how that improved our design in a realistic way is that we went back to MotorSolve and we took our temperatures. David actually ran 2 solutions on here. He took the did a simulation, thermal simulation on the pre-optimization design, and then again on the post-optimization design. And we took those temperatures component by component, put them back into MotorSolve, where MotorSolve could run the electromagnetic simulation again, but using those new temperatures on the components instead of just the default room temperature that we used initially. And MotorSolve has material information to know how material properties change with temperature in the vast majority of its material library. This allowed us to evaluate the design, not just how did our geometry improve it, but how did they improve geometry leading to reduced losses, leading to cooler temperatures, which in turn also lead to increased performance. And so we reran the simulations at the tested temperature. And what we found was that actually the temperature reduction, not only did we see that initial from geometry 40-odd% increase in output power, we were getting closer almost to 50% increase in power and torque once not only is the geometry better, but the cooling is better. We're keeping everything lower. So we're seeing a much better improvement overall from the machine. If we're going for a longer design phase where maybe we're now going to take this design that we're fairly confident in from the electromagnetic perspective, we're confident in from the thermal perspective, and we want to hand it off maybe to our mechanical or acoustics teams. From the design perspective of the electromagnetics, magnetics, and the thermals, we'd be happy to sign off that yes, this is an improved design. And of course, this took, as we mentioned, about 19 hours of electromagnetic optimization that was all automated. And then I guess for the 2 runs here, about 11 hours each of CFD analysis, and we're happy with it. is a very effective use of our time, effective use of our licenses and engineer time as well, being able to step away. And of course, we had some involvement in between, David, taking the model and setting it up. For a larger scale, as we mentioned, HEEDS could have automated a lot of that. Once you've done it once, if you know how to do it by hand, you can tell HEEDS how to do it. So, one last question to the audience. When you're looking at thermal behavior, where are your priorities? Because for us, we were looking at temperatures to avoid demagnetization, but to improve performance. And performance is really the driving factor in here. But we have a lot of users of our software who might be looking just to avoid damage, demagnetization or degradation in the materials. We also have a lot of them who need to define the operating conditions. How cold does our coolant need to be? How much power can we afford to push through this machine in terms of losses before things heat up too much? So again, I'm curious to see what you guys have in terms of concerns. Again, other is an option here because obviously the first three options are not all encompassing. Right. Okay, so everybody's interested in the first three options that we gave here. There's a lot of interest in avoiding damage and demagnetization. That's not a surprise given how often we talk about that with users and customers, and defining operating conditions. That surprised me, although just in terms of its share, but that's good. This is something that's important in the design process, not just reevaluation, but for people who are looking in that initial design. So we're getting right towards the end of our presentation here, and we want to leave time for everyone to ask questions if there's questions. So we'll just quickly go through one quick note, one quick slide, which is that you can do multi-physics. Now today, we've talked about Simcenter 3D, Simcenter NX being the underlying CAD package on it that we have. David was using for the thermal analysis. It also has electromagnetic capabilities. So Simcenter MotorSolve uses the same electromagnetic solver that's available in Simcenter 3D. But we can expand that. We look today at thermals, but the same package can look at structural analysis, vibroacoustics, all these different domains. And again, we can connect them all, we can automate them all using HEEDS. And this allows us to really be effective with our time when we're looking at a design going from electromagnetics through the different physics domains that are of interest to us. Yep, so intelligent design and space exploration or optimization. That's HEEDS, connects into all of this. And it's really useful for making sure that we don't waste, we use it internally to make sure that we're not wasting too much time when we're working on projects. So just a quick recap, we just initially took a look at what physics are interesting for electric motor simulation. We decided to focus on electromagnetics and thermals for today. We went over the electric motor development process, what tools we're using, how we're stepping through those different tools. Looked at a basic electromagnetic model of a motor in Simcenter MotorSolve, built a basic template model, and handed that off into Simcenter HEEDS that allowed us to do optimization on that design. From there, David took over, did further thermal design analysis, where we could see the results of our electromagnetic optimization on the thermal behavior of our machine. After that, as we quickly mentioned, we could, of course, have continued on to structural or acoustics or any other physics domain that we're interested in. I'm getting flagged here that we're running low on time. So thank you, everyone, very much for coming, for listening, for putting up with us talking for so long. If you have any questions, please throw your questions into the webinar's question or chat functionality. If you want to get in touch with us, you can, of course, visit MyHET's website. There's a contact us link there as well and a QR code. Or if you want to talk to David or myself, about the work that we did on this or how we could use our tools to help you with your projects, our email addresses are right there. Please feel free to shoot us an email and we would be happy to help you out with that. Now, Anthony, are there any questions for us?
Yeah, great. Thanks, Anthony. Just having a look here. There are a couple of questions, so we can start with this one here. Okay, so for the optimization processes, you have one, can they be parallelized?
Right. So I guess I did mention that we used a single license, single core during our electromagnetic optimization. That was just because that was what was easy for me to set up in the background on my workstation. If you have the license capability, so if you have sufficient licenses or the license features to use multiple cores or multiple instances at once, Heeds is perfectly happy to run parallelized design exploration. So we could have told it, hey, use 5 different licenses, go run 5 designs at the same time. It wasn't necessary for this project, so we didn't use that.
One more here that I'm seeing, could the optimization happen on the cooling design?
David, do you want to speak to that?
Yeah, could you reread that? Does it the optimization, does it apply to the cooling? Is that what the question was?
Yeah, could it be performed on the cooling design?
Oh yes, absolutely. Especially in FLOEFD, where you have you actually can integrate FLOEFD with speed in a number of different ways to directly modify the CAD geometry to see how that affects the cooling as well. And then you could certainly couple that back to another solution in MotorSolve as well.